basically taking unit Gaussian data and I'm forwarding it through the network. And with this particular initialization strategy, where right now that initialization strategy is what I described in the previous slide. So you sample from unit Gaussian and you scale it by 0.01. So what I'm doing here in this for loop is I'm forward propagating this network, which is right now made up of just a series of layers of the same size. So we have 10 layers of 500 neurons on each layer. And I'm forward propagating with this initialization strategy for a unit Gaussian data. And what I want to look at is what happens to the statistics of the neurons activations throughout the network with this initialization. So we're going to look specifically at the mean and the standard deviation, and we're going to plot the mean standard deviation, and we're going to plot the histograms. So we take all this data through, and then say at the 5th layer, we're going to look at what values the neurons take on in, say, the 5th or 6th or 7th layer, and we're going to make histograms of those. So with this initialization, if you run this experiment, it ends up looking as follows. So here I'm printing it out. We start off with a mean of 0 and standard deviation of 1. That's our data. And now I'm forward propagating. And as I go to the 10th layer, look at what happens to the mean. We're using 10H. So 10H is symmetric. So as you might expect, the mean stays around 0. But the standard deviation, look at what happens to it. It started off at 1. And suddenly the standard deviation goes to 0.2, then 0.04, and it just plummets down to 0. So the standard deviation of these neurons just goes down to 0. Looking at the histograms here at every single layer, at the first layer, the histogram is reasonable. So we have a spread of numbers between -1 and 1. And then what ends up happening to it, this just collapses to a tight distribution at exactly 0. So what ends up happening with this initialization for this 10-layer network is all the 10H neurons just end up outputting just 0. So at the last layer, these are tiny numbers of like near 0 values. And so all activations basically become 0. And why is this an issue? Okay, so think about what happens to the dynamics of the backward pass, to the gradients. When you have tiny numbers in the activations, your x's are tiny numbers on the last few layers. What do these gradients look like on the weights in these layers? And what happens to the backward pass? So first of all, suppose so there is a layer here that looks at some layer before it, and almost all the inputs are tiny numbers. That's the x. X is a tiny number. What is the gradient? What might you expect the gradients for the w to be in that case for those layers?
Very small.
Sorry, you said very small?
Yeah.
So why would they be very small?
X is the gradient for w.
That's right. So the gradient for w will be equal to x times the gradient from the top. Yeah. Okay. And so if x are tiny numbers, then your gradients for w are tiny numbers as well. And so these guys will basically have almost no gradient accumulated. Now, we can also look at what happens with these matrices. Again, we took data that was distributed as a unit Gaussian in the beginning, and then we ended up multiplying it by w and activation function. And we saw that basically everything goes to 0. This just collapses over time. And think about the backward pass as we chain the gradient through these layers in backpropagation. What we're doing effectively is some of the gradient kind of forks off into our gradient w, and we saw that those are tiny numbers. But then through backpropagation, we're going through gradients of x. And so what we end up doing when we backprop through here is we again end up multiplying by w again and again at every single layer. And if you take unit Gaussian data and you multiply it by w's at this scale, you can see that everything goes to 0. And the same thing will happen in backward pass. We're successively multiplying by w as we backpropagate into x on every single layer. And as we do that, this gradient, which started off with reasonable numbers from your loss function, will end up just going towards 0 as you keep doing this process. And you end up with gradients here that are basically just tiny, tiny numbers. And so you basically end up with very, very low gradients throughout this network because of this reason. And this is something that we refer to as vanishing gradient. As this gradient travels through, with this particular initialization, you can see that the magnitude of the gradient will just go down when we used this initialization for w of 1e-2. Okay? So we can try a different extreme. Instead of scaling here as we scaled with 1e-2, we can try a different scale of the w matrix at initialization. So suppose I try 1.0 instead of 0.01. We'll see another funny thing happen, because now we've overshot the other way in a sense that you can see that, well, maybe it's best to look at the distributions here. You can see that everything is completely saturated. These 10H neurons are either all -1 or all 1. I mean, the distribution is really just, everything is super saturated. Your entire network, all the neurons throughout the network are either -1 or 1, because the weights are too large and they keep oversaturating the 10H neurons, because the scores that end up going through the nonlinearity are just very large, because the weights are large. And so everything is super saturated. So what are the gradients flowing through your network? It's just terrible. It's a complete disaster, right? It's just zeros for just exponentially zero, and you die. So you can train for a very long time, and what you'll see when this happens is your loss is just not moving at all, because nothing is backpropagating, because all the neurons are saturated and nothing is being updated. Okay? So this initialization, as you might expect, actually is like super tricky to set, and it needs to be kind of, in this particular case, it needs to be somewhere between 1 and 0.01. Okay? And so you can be slightly more principled instead of trying different values, and there are some papers written on this. So for example, in 2010, there was a proposal for what we now call the Javier initialization from Glorot et al. And they kind of went through and they looked at the expression for the variance of your neurons. And you can write this out, and you can basically propose a specific initialization strategy for how you scale your gradients. So I don't have to try a 0.01. I don't have to try 1 or whatever else. So they recommend this kind of initialization where you divide by the square root of the number of inputs for every single neuron. So if you have lots of inputs, then you end up with lower weights. And intuitively that makes sense, because you're doing more weight, you have more stuff that goes into your weighted sum, so you want less of an interaction to all of them. And if you have smaller number of units that are feeding into your layer, then you want larger weights, because then there's only a few of them and you want to have a variance of 1. So just to back up a bit, the idea here is they were looking at a single neuron, no activation functions included, it's just a linear neuron. And all they're saying is if you're getting unit Gaussian data as input, and you'd like this linear neuron to have a variance of 1, then you should initialize your weights with this amount. And in the notes, I go into exactly how this is derived. It's just some math with standard deviations. And basically, this is a reasonable initialization. So I can use that instead. And you can see that if I use it here, the distributions end up being more sensible. So we're again looking at the histogram between -1 and 1 of these 10H units. And you get a more sensible number here. And you actually have, you're within the active region of all these 10Hs. And so you can expect that this will be a much better initialization because things are in the active regions and things will train from the start. Nothing is super saturated in the beginning. The reason that this doesn't just end up being very nice, and the reason we still have convergence down here, is because this paper doesn't take into account the nonlinearities, in this case the 10H. And so the 10H nonlinearity ends up like kind of deforming your statistics of the variance throughout. And so if you stack this up, it ends up still doing something to the distribution. In this case, it seems that the standard deviation goes down, but it's not as dramatic as if you were to set this by just trial and error. And so this is like a reasonable initialization to use in your neural networks compared to just setting it to 0.01. And so people end up using this in practice sometimes. But, so this works in the case of 10H, does something reasonable. It turns out if you try to put it into a rectified linear unit network, it doesn't work as well. And the decrease in the standard deviations will be much more rapid. So looking at a ReLU neuron, in the first layer, it has some distribution. And then this distribution, as you can see, just gets more and more peaky at 0. So more and more neurons are not activating with this initialization. So using the Javier initialization in a rectified layer net does not do good things. And so again, thinking about this paper, they don't actually talk about nonlinearities. And the ReLU neurons, they compute this weighted sum, which is within their domain here. But now after the weighted sum, you do a ReLU. So you kill half of the distribution, you set it to 0. And intuitively, what that does to your distribution of your outputs is it basically halves your variance. And so it turns out, as was proposed in this paper just last year, in fact, someone said basically, look, there's a factor of 2 you're not accounting for, because these ReLU neurons, they effectively half your variance each time, because you take everything, like say you have unit Gaussian inputs, you take them through your nonlinearity, you have unit Gaussian stuff out, but now you ReLU that, and so you end up halving the variance. So you need to account for it with an extra 2. And when you do that, then you get proper distributions specifically for the ReLU neuron. And so in this initialization, where if you're using ReLU nets, you have to worry about that extra factor of 2, and everything will come out nicely. And you won't get this factor of 2 that keeps building up and it screws up your activations exponentially. Okay? So basically, this is tricky stuff, and it really matters in practice. In practice, in their paper, for example, they compare having the factor of 2 or not having that factor of 2. And it matters when you have really deep networks. In this case, I think they had a few dozen layers. If you account for the factor of 2, you converge. If you don't account for that factor of 2, does nothing. It's just zero loss. Okay? So very important stuff. You really need to think it through. You have to be careful with the initialization. If it's incorrectly set, bad things happen. And so specifically in the case, if you have neural networks with ReLU units, there's a correct answer to use, and that's this initialization from Kaiming. Okay, so tricky stuff. This is partly why neural networks didn't work for a long time. Is I think people didn't fully maybe appreciate just how difficult this was to get right, and tricky. And so I'd just like to point out that proper initialization, basically, active area of research. You can see that papers are still being published on this. A large number of papers just proposing different ways of initializing your networks. These last few are interesting as well because they don't give you a formula for initializing. They have these data-driven ways of initializing the networks. And so you take a batch of data, you forward it through your network, which is now an arbitrary network, and you look at the variances at every single point in your network. And intuitively, you don't want your variances to go to 0. You don't want them to explode. You want everything to have roughly, say, like be a unit Gaussian throughout your network. And so they iteratively scale these weights in your network so that you have roughly unit Gaussian activations everywhere, or on the order of that, basically. And so there are some data-driven techniques and a line of work on how to properly initialize. Okay, so I'm going to go into a technique that alleviates a lot of these problems, but right now I could take some questions if there are any at this point. Go ahead.
Would it make any sense to standardize the gradient coming in by dividing by the variance or something?
Would it make sense to standardize the gradient coming in by dividing by the variance? Possibly, but then you're not doing backpropagation, because if you meddle with the gradient, then it's not clear what your objective is anymore, and so you're not getting necessarily gradient. So that's maybe the only concern. I'm not sure what would happen. You can try to normalize the gradient. I think the method I'm going to propose in a bit is actually doing something to the effect of that, but in a clean way. Okay, cool. So let's go into something that actually fixes a lot of these problems in practice. It's called batch normalization, and it was only proposed last year. And so I couldn't even cover this last year in this class, but now I can. And so this actually helps a lot, okay? And the basic idea in batch normalization paper is, okay, you want roughly unit Gaussian activations in every single part of your network. And so just do that. Just make them unit Gaussian, okay? You can do that because making something unit Gaussian is a completely differentiable function. And so it's okay. You can backpropagate through it. And so what they do is, you're taking a mini batch of your data and you're taking it through your network. We're going to be inserting these batch normalization layers into your network. And the batch normalization layers, they take your input X, and they make sure that in every single feature dimension across the batch, you have unit Gaussian activations. So say you have a batch of 100 examples going through the network. Maybe this is a good example here. So you have a batch of activations. So you have n things in your mini batch, and you have d features or d activations of neurons that are at some part. And this is an input to your batch normalization layer. So this is a matrix of X of activations. And batch normalization effectively evaluates the empirical mean and variance along every single feature, and it just divides by it. So whatever your X was, it just makes sure that every single column here is a unit Gaussian. And so that's a perfectly differentiable function, and it just applies it at every single feature or activation independently across the batch. Okay? So you can do that, and turns out to be a very good idea. Now, one problem with this scheme, so this is the way this will work, is normally we have fully connected followed by nonlinearity, fully connected followed by nonlinearity, and we have a deep network of this. Now we're going to be inserting these batch normalization layers right after fully connected layers, or equivalently after convolutional layers, as we'll see soon with convolutional networks. And basically, we insert them there, and they make sure that everything is roughly unit Gaussian at every single step of the network, because we just make it so. And one problem you might think of with this is that seems like an unnecessary constraint. So when you put a batch normalization here after fully connected, the outputs will definitely be unit Gaussian because you normalize them. But it's not clear that 10H actually wants to receive unit Gaussian inputs. So if you think about the form of 10H, it has a specific scale to it. It's not clear that a neural network wants to have this hard constraint of making sure that batch norm outputs are exactly unit Gaussian before the 10H. Because if you'd like the network to pick if it wants your 10H outputs to be more or less diffuse, more or less saturated. And right now, it wouldn't be able to do that. So a small patch on top of it, this is the second part of batch normalization, is not only do you normalize X, but after normalization, you allow the network to shift by gamma and add a B for every single feature input. And so what this allows the network to do, and these are all parameters. So gamma and B here are parameters that we're going to backprop into. And they just allow the network to shift. After you've normalized to unit Gaussian, they allow this bump to shift and scale if the network wants to. And so we initialize though presumably with 1 and 0 or something like that. And then the network can choose to adjust them. And by adjusting these, you can imagine that once we feed into 10H, the network can choose through the backprop signal to make the 10H more or less peaky or saturated in whatever way it wants. But you're not going to get into this trouble where things just completely die or explode in the beginning of optimization. And so things will train right away, and then backpropagation can take over and can fine-tune it over time. And note one more important feature, by the way, is that if you set these gamma and B, if you train them, if by backpropagation it happens that they end up taking the empirical variance and the mean, then you can see that basically the network has the capacity to undo the batch normalization. So this part can learn to undo that part. And so that's why batch normalization can act as an identity function, or it can learn to be an identity, whereas before it couldn't. And so when you have these batch norm layers in there, the network can, through backpropagation, learn to take it out, or it can learn to take advantage of it if it finds it helpful. Through the backprop, this will kind of work out. So that's just a nice point to have. And so basically, there are several nice properties to batch norm. So this is the rough algorithm, as I described. Nice properties are that it improves the gradient flow through the network. It allows for higher learning rates, so your network can learn faster. It reduces, this is an important one, it reduces the strong dependence on initialization. As you sweep through different choices of your initialization scale, you'll see that with and without batch norm, you'll see a huge difference. With batch norm, you'll see a much more, things will just work for much larger settings of the initial scale. And so you don't have to worry about it as much. It really helps out with this point. And one kind of more subtle thing to point out here is it kind of acts as a funny form of regularization. And it reduces need for dropout, which we'll go into in a bit later in the class. But the way it acts as a funny regularization is with batch norm, when you have some kind of an input X and it goes through the network, then its representation at some layer in the network is basically not only a function of it, but it's also a function of whatever other examples happen to be in your batch. So because whatever other examples are with you in that batch, normally these are processed completely independently in parallel, but batch norm actually ties them together. And so your representation at, say, like the fifth layer of a network is actually a function of whatever batch you happen to be sampled in. And what this does is it jitters your place in the representation space on that layer. And this actually has a nice regularizing effect. And so this jittering stochastically through this batch that you happen to be in has this effect. And so I realize it's hand-wavy, but actually seems to actually help out a bit. OK, and at test time, batch norm layer, by the way, functions a bit differently. You don't want to, at test time, you want this to be a deterministic function. So just a quick point that at test time, when you're using a batch norm layer, it functions differently. In particular, you have this mu and a sigma that you keep normalizing by. So at test time, you just remember your mu and sigma across the data set. You can either compute it, like what is the mean and the sigma at every single point in the network. You can compute that once over your entire training set, or you can just have a running sum of mu's and sigmas while you're training, and then make sure to remember that in the batch norm layer. Because at test time, you don't want to actually estimate the empirical mean and variance across your batch. You want to just use those directly. Okay? So because this gives you a nice deterministic function forward at test time. So that's just a small detail. OK, and so that's batch norm. Any questions about batch norm, by the way? So this is a good thing. Use it. And you'll implement it actually in your assignment. Go ahead.
How does it affect the runtime? Does it slow things down at all?
Thank you. So the question is, does it slow down things at all? It does. So there is a runtime penalty that you have to pay for it, unfortunately. I don't know exactly how expensive it is. I heard someone say a value of like 30% even. And so I don't know actually, I haven't fully checked this, but basically there is a penalty because you have to do this at normally it's very common to basically have a batch norm layer after every convolution layer. And when you have, say, 150 like layers, you end up having all this stuff build up. Any other questions? That's the price we pay, I suppose. Go ahead.
Is there a way of telling, like, if you don't use batch normalization, if your data's not going so well, and that maybe it would be a good idea to try it?
So when can you tell that you maybe need batch norm? I think I'll come back to that in a few slides. We'll see, like, how can you detect that your network is not healthy? And then maybe you want to try batch norm. OK, so the learning process, I have 20 minutes. I think I can do this. Yeah, we're at slide 70 out of 100, so I think we're fine. OK, so we've pre-processed our data. We've decided, let's decide on some, for these purposes of these experiments, I'm going to work with CFAR10, and I'm going to use a 2-layer neural network with, say, 50 hidden neurons. And I'd like to give you an idea about like how this looks like in practice when you're training neural networks. Like, how do you play with it? Where are some of the, how do you actually converge to good hyperparameters? What does this process of playing with the data and getting things to work look like in practice? And so I decided to try out a small neural network. I've pre-processed my data. And so the first kinds of things that I would look at if I want to make sure that my implementation is correct and that things are working, first of all, so I'm going to be initializing here a 2-layer neural network. So weights and biases initialized with just naive initialization here, because this is just a very small network, so I can afford to maybe do just a naive sample from a Gaussian. And then this is a function that basically is going to train a neural network. And I'm not showing you the implementation, obviously. But just one thing, basically it returns your loss and it returns your gradients on your model parameters. And so the first thing I might try, for example, is I disable the regularization that's passed in the end. And I make sure that my loss comes out correct, right? So I mentioned this in previous slides. So say I have 10 classes in CFAR10. I'm using softmax classifier, so I know that I'm expecting a loss of negative log of 1/10, because that's just the expression for the loss, and that turns out to be 2.3. And so I put this in, I get a loss of 2.3. So I know that basically the neural network is currently giving me a diffuse distribution over the classes because it doesn't know anything. We've just initialized it. So that checks out. The next thing I might check is that, for example, I crank up the regularization, and I of course expect my loss to go up, right? Because now we have this additional term in the objective. And so that checks out. So that's nice. The next thing I would usually try to do, it's a very good sanity check when you're working with neural networks, is try to take a small piece of your data and try to make sure you can overfit your training data. Just that small piece. So I'm going to take, like, say, a sample of like 20 training examples and 20 labels. And I just make sure that I train on that small piece. And I just make sure that I can get a loss of basically near 0. I can fully overfit that. Because if I can't overfit a tiny piece of my data, then things are definitely broken. And so here I'm starting the training, and I'm starting with some random number of parameters here. I'm not going to go into full details there. But basically, I make sure that my cost can go down to 0, and that I'm getting accuracy of 100% on this tiny piece of data. And so that gives me confidence that probably backprop is working. Probably the update is working. The learning rate is set somehow reasonably. And so I can overfit a small data set, and I'm happy at this point. And maybe I'm thinking about now scaling up to larger data. Go ahead.
So what if we are unable to like overfit it? So should
then
we increase the number of neurons? Or?
So you should be able to overfit. Sometimes I even try, like, say, like 1 or 2 or 3 examples. You can really crank this down. And you should be able to overfit, even with smaller networks. And so that's a very good sanity check, because you can afford to have small networks, and you just make sure you can overfit. If you can't overfit, your implementation is probably incorrect. Something is very funky is wrong. So you should not be scaling up to your full data set before you can pass the sanity check. So let's see. So basically, the way I try to approach this is take your small piece of data, and now we're scaling it up. We've overfitted, so now I'm scaling up to like the bigger data set. And I'm trying to find the learning rate that works. And you have to really play with this, right? You can't just eyeball the learning rate. You have to find the scale, roughly. So I'm trying first a small learning rate, like 1e-6. And I see that the loss is barely going down. So this learning rate of 1e-6 is probably too small, right? Nothing is changing. Of course, there could be many other things wrong, because your loss could be constant for like a million reasons. But we've passed a small sanity check, so I'm thinking that this is probably loss is too low, and I need to tune it. By the way, this is a fun example here of something funky going on that is fun to think about. My loss just barely went down, but actually my training accuracy shot up to 20% from the default 10%. How does that make any sense? How can I be, my loss just barely changed, but my accuracy is so good? Well, much better than 10%. How is that even possible?
Yes, you identified
Sorry?
it correctly, but you're not differentiating it by a lot with respect to the second prediction that you're making for each image.
The regularization term is still the major.
The regularization term is still,
Major component of the loss.
yeah, maybe. Not quite, I think, what I'm looking for. Go ahead.
Softmax loss is logarithmic,
Okay.
so a slight increase in performance won't translate into much of a difference in loss.
Okay, a bit, maybe. Not quite. So think about how accuracy is computed and how this cost is computed, right? Go ahead.
I think it's because it's just looking at which one's the highest for the accuracy, and so the probabilities are just shifted a little bit. You'll still have really high loss even if the accuracy is
Right. So you start out with a fuse scores, and now what's happening is you're training. So these scores are tiny shifting. Your loss is still roughly diffuse, so you end up with the same loss, but now your correct answers are now tiny bit more probable. And so when you're actually computing the accuracy, the argmax class ends up being the correct one. So these are some of the fun things you run into when you actually train some of this stuff. You have to think about the expressions. Okay, so now I tried very low learning rate. Things are barely happening. So now I'm going to go to the other extreme, and I'm going to try out a learning rate of 1 million. What could possibly go wrong? So what happens in that case is you get some weird errors, and things explode. You get nans. Really fun stuff happens. So okay, 1 million is probably too high, is what I'm thinking at this point. So then I try to narrow in on rough region that actually gives me a decrease in my cost, right? That's what I'm trying to do with my binary search here. And so at some point I get some idea about, roughly where should I be cross-validating, okay? Hyperparameter optimization, at this point I'm trying to find the best hyperparameters for my network. What I really like to do in practice is go from coarse to fine strategy. So first I just have a rough idea by playing with it where the learning rate should be. Then I do a coarse search over learning rates of like a bigger segment. And then I repeat this process. So I look at what works, and then I narrow in on the regions that work well, okay? Do this hierarchically. And in your code, for example, detect explosions and break out early. That's like a nice tip in terms of the implementation. So what I'm doing effectively here is I have a loop where I sample my hyperparameters, say in this case the regularization and the learning rate. I sample them, I train, I get some results here. So these are the accuracies in the validation data, and these are the hyperparameters that produce them. And some of the accuracies you can see that they work quite well. So 50%, 40%, some of them don't work well at all. So this gives me an idea about what range of learning rates and regularizations are working relatively well. And when you do this hyperparameter optimization, you can start out first with just a small number of epochs. You don't have to run for a very long time. Just run for a few minutes. You can already get a sense of what's working better than some other things. And also, one note, when you're optimizing over regularization and learning rate, it's best to sample from log space. You don't just want to sample from a uniform distribution, because these learning rates and regularization, they act multiplicatively on the dynamics of your backpropagation. And so that's why you want to do this in log space. So you can see that I'm sampling from -3 to -6, the exponent for the learning rate, and then I'm raising it to the power of 10. I'm raising 10 to the power of it. And so you don't want to just be sampling from a uniform of 0.01 to like 100, because then most of your samples are kind of in a bad region, right? Because the learning rate is a multiplicative interaction. So something to be aware of. Now, once I found what works relatively well, I'm, of course, doing a second pass where I'm kind of going in and I'm changing these again a bit, and I'm looking at what works. So I find that I can now get to 53. So some of these work really well. One thing to be aware of, sometimes you get a result like this. So 53 is working quite well. And this is actually, if I see this, I'm actually worried at this point. Because so through this cross-validation here, I have a result here. And there's something actually wrong about this result that hints at some issue. There's an unsettling problem with this result.
Local optimum is not necessarily global optimum.
A local optimum is not necessarily global optimum. So what makes you say that exactly?
Because you're seeing 2 peaks.
Oh, I see. So you're saying that actually they're quite diffuse in a sense, like they're not consistent too much. Yeah, perhaps. Okay, so in interest of time, what's happening here, look, I'm optimizing learning rate between -3 and -4, 10 to the, and I end up with a very good result that is just at the boundary of what I'm hyperparameter optimizing over. So this is almost 1e -3, it's almost 0.001, which is really a boundary of what I'm searching over. So I'm getting a really good result at an edge of what I'm looking for, and that's not good because maybe this edge here, the way I've defined it, is not actually optimal. And so I want to make sure that I spot these things and I adjust my ranges, because there might be even better results going slightly this way. So maybe I want to change -3 to -2 or 2.5. But for regularization, I see that 1e -4 is working quite well. So maybe I'm in a slightly better spot and so on. So worry about this. One thing also I'd like to point out is you'll see me sample these randomly. So 10 to the uniform of this. So I'm sampling random regularization and learning rates when I'm doing this. What you might see sometimes people do is what's called a grid search. So really the difference here is instead of sampling randomly, people like to go in steps of fixed amounts in both the learning rate and the regularization. And so you end up with this double loop here over some settings of learning rate and some settings of regularization because you're trying to be exhaustive. And this is actually a bad idea. It doesn't actually work as well as if you sample randomly. And it's unintuitive, but you actually always want to sample randomly. You don't want to go in fixed steps. And here's the reason for that. It's kind of, you need to think about it a bit. But this is the grid search way. So I've sampled at set intervals, and I kind of have confidence that I've, sweeped out this entire space. And as opposed to random sampling, where I've just randomly sampled from the two. The issue is that in hyperparameter optimization and training neural networks, what often happens is that one of the parameters can be much, much more important than the other parameter. Okay, so say that this is an unimportant parameter. Its performance, the performance of your loss function, is not really a function of the y dimension, but it's really a function of the x dimension. You get much better results in a specific range along the x-axis. And if this is true, then, which is often the case, then in this case, you're actually going to end up sampling lots of different x's, and you end up with a better spot than here, where you've sampled at exact spots and you're not getting any kind of information across the x, if that makes sense. So always use random, because in these cases, which are common, the random will actually give you more bang for the buck. Okay. So there are several hyperparameters you want to play with. The most common ones are probably the learning rate, the update type, maybe. We're going to go into this in a bit. The regularization and the dropout amounts, which we're going to go into. So this is really, it's so much fun. So in practice, what this looks like is we have, for example, a computer vision cluster. We have 70 machines, so I can just distribute my training across 70 machines. And I've written myself, for example, a command center interface where these are all the loss functions on all the different machines in our computer vision cluster. These are all here hyperparameters I'm searching over. And I can see basically what's working well and what isn't, and I can send commands to my workers, and I can say, okay, this isn't working at all, so just resample, you're not doing well at all. And some of these are doing very well, and I look at what's exactly working well, and I'm adjusting. It's a dynamic process that I have to go through to actually get this stuff to work well, because you just have too much stuff to optimize over, and you can't afford to just spray and pray. You have to work with it. Okay, so you're optimizing, and you're looking at the loss functions. These loss functions can take various different forms, and you need to be able to read into what that means. So you'll get quite good at looking at loss functions and intuiting what happens. So this one, for example, as was pointing out in the previous lecture, it's not as exponential as I'm maybe used to my loss functions. I'd like it to, it looks a little too linear, and so that maybe tells me that the learning rate is maybe slightly too low. So that doesn't mean the learning rate is too low. It just means that I might want to consider trying a higher learning rate. Sometimes you get all kinds of funny things. So you can have a plateau where at some point the network decides that it's now ready to optimize. Usually, so what is the prime suspect in these kinds of cases? Just a guess, maybe? Sorry?
The weights are initialized at some plateau?
Yeah, sure. So weights initialization, I think, is the prime suspect. You've initialized them incorrectly, the gradients are barely flowing, but at some point they add up and it just suddenly starts training. So lots of fun. In fact, it's so much fun that I started an entire Tumblr a while ago on loss functions. So you can go through these. So people contribute these, which is nice. And so this is, I think, someone training a spatial transformer network. We're going to go into that. This is all kinds of exotic shapes. I'm not, at some point you're not really sure what any of this means. It's going so well. Yeah, so here, this is again like several tasks that are training at the same time, and just this, by the way, I know what happened here. It's this is actually training a reinforcement learning agent. The problem in reinforcement learning is you don't have a stationary data distribution. You don't have a fixed data set. In reinforcement learning, you're an agent interacting with the environment. If your policy changes and you end up like staring at the wall, or you end up looking at different parts of your space, you end up with different data distributions. And so suddenly, I'm looking at something very different than what I used to be looking at, and I'm training my agent, and the loss goes up because the agent is unfamiliar with that kind of inputs. And so you have all kinds of fun stuff happening there. And then, this one is one of my favorites. I have no idea what basically happened here. This loss oscillates, but roughly does. And then it kind of just explodes. Clearly something was not fully right in this case. And also here, it just kind of at some point decides to converge. I have no idea what was wrong. So you get all kinds of funny things. If you end up with funny plots in your assignments, then please do send them to lossfunctions.tumblr. We'll post them. So during training, don't only look at the loss function. Another thing to look at is your accuracies, especially accuracies, for example. So you sometimes prefer looking at accuracies over loss functions because accuracies are interpretable. I know what these classification accuracies mean in absolute terms, whereas for loss function, it's maybe not as interpretable. And so in particular, I have an accuracy curve for my validation data and my training data. And so for example, in this case, I'm seeing that my training data accuracy is getting much, much better, and my validation accuracy has stopped improving. And so based on this gap, that can give you hints on what might be going on under the hood. In this particular case, there's a huge gap here, so maybe I'm thinking I'm overfitting. I'm not 100% sure, but I might be overfitting. I might want to try to regularize more strongly. One of the things you might also be looking at is tracking the difference between the scale of your parameters and the scale of your updates to those parameters. So say suppose that your weights are on the order of unit Gaussian distributed, then intuitively the updates that you're incrementing your weights by in backpropagation, you don't want those updates to be much larger than the weights, obviously, or you don't want them to be tiny. Like you don't want your updates to be on the order of 1e-7 when your weights are on the order of 1e-2. And so look at the update that you're about to increment onto your weights and just look at its norm, for example, the sum of squares, and compare it to the rough scale of your parameters. And usually a good rule of thumb is this should be roughly 1e-3. So basically every single update you're modifying on the order of like a third significant digit for every single parameter, right? You're not making huge updates, you're not making very small updates. So that's one thing to look at. Roughly 1e-3 usually works okay. If this is too high, I want to maybe decrease my learning rate. If it's way too low, like say it's 1e-7, maybe I want to increase my learning rate. And so in summary, today we looked at a whole bunch of things to do with training neural networks. The TLDRs of all of them are basically use ReLUs for image to subtract mean, use the Javier initialization, or if you think you have a smaller network, you can maybe get away with just choosing your scale to be 0.01, or maybe you want to play with that a bit. There's no strong recommendation here, I think. Batch normalization, just use. And when you're doing hyperparameter optimization, make sure to sample your hyperparameters and do it in log space when appropriate. And that's something to be aware of. And this is what we still have to cover, and that will be next class. We do have 2 more minutes, so I will take questions if there are any. Go ahead.
There is like some correlation between the regularization and the learning rate. Is there any way to like know how they're going to like correlate with each other, so you're not just like randomly choosing them, or just randomly like the best way?
Yeah, so you're asking about the correlation between regularization and the learning rate. You optimize over both of them during hyperparameter optimization, right? And you're trying to decouple them, but maybe I don't think there's any obvious thing I can recommend there. You have to guess and check a bit. I don't think that anything jumps out at me that's obvious on how to decouple them. Okay, great. No more questions. We're done.
a quick question regarding the assignment.